And good afternoon, wherever you may be in your day. As always, thank you for choosing to make general chemistry part of your day. So, we're going to talk about the four quantum numbers. And in many ways, I kind of just want you to sit and digest this next 15 minutes of chemistry. The next day's video, where we apply this specifically to elements, the periodic table, and electron configurations, should help all this click in. So there's going to be a lot of stuff dumped on you here, and we're not going to apply any of it. With that being said, let's go into where we left off. The idea that electrons can be waves and particles from the de Broglie equation. If you notice, I just kind of went through that super fast because it's more historical than perhaps practical. We have so many things to cover in 101. That's not really one I care to do too much with, but I did want to talk about it. So coming back to that idea, if we assume that an electron is a wave and a particle, and then we assume that it only acts as a standing wave, meaning only certain ways can you swing a rope tied to a wall to get a stable structure. So you can do it like this, you can do it like this. You can see me, I'm very happy, very excited about doing this. I got a little bow tie on. And then we do some math. We do lots of math. Then we do some more math. Then we solve the math. And we get something that looks like a pitchfork. It's a wave function. Or probability. So we solve all this math, and again, I don't really, for Chem 101, whatever. But the solving of all this math gives us an orbital. So let me talk a little bit about what an orbital really is. I looked up the Wikipedia definition of an orbital, and it's almost useless. I'm going to use this definition: 3D probability cloud that contains an electron. But let me do an analogy. Let's say we have a house, we've put in an electric fence, and we have a puppy dog. Or we're a puppy dog. Let's pretend we're a puppy dog. There we go, I'm a puppy dog. Okay, and I get kicked out of the house. Or actually, we're not the puppy dog, we're the owner. We kick a puppy dog out of the house, we're inside the house, we don't have any windows, terrible build. I know, we need better architects. So we're in there. Do we know where the dog is? Well, there's a high probability, right? The dog is within the electric fence. Doesn't have to be. Battery could have died. Dog could have decided it wanted to fry itself and run through that. But we're reasonably sure it's inside the shape of the electric fence. This is the electron. We're reasonably sure, quantum mechanic calculations tells us the electron could literally be anywhere in the universe, but we're reasonably sure that it's within this shape. Instead of an electric fence, that's what our orbital is. Now, within the orbital, the electron doesn't spend the same amount of time everywhere. Just like the dog. We could be reasonably sure the dog rarely goes in the middle of our lake. Just not a happy place for a dog. We could also reasonably be assured that the dog is not in the middle of the trunk of a tree. If we had thorn bushes, don't throw me in the briar patch. Whatever you do, don't throw me in the briar patch. We could be reasonably sure the dog's probably not in the briar patch. The dog has places it might like. It might like its food bowl. It might like its water bowl. It might like to beg at the door. It may like to chase squirrels up a tree and bark at them. There are places the dog might like to be more than others. And same thing with the electron. The electron is not equally dispersed within the orbital. There are places it is much more likely to be than others. But again, if we're inside the house and we don't have a window, we don't know where the dog is. We can guess. We can give the probability of the dog being a certain place. And that's what we're doing with the electron. So if we were to just trace out the dog's movements all day long, it really likes to chase squirrels. Around the food bowl, go out here, chase some cars. And we would start to do what? We would start to create a map of where the dog would be. And this shape that gets carved out would become the orbital itself, with the high probability, say 90% probability, of the dog being within that contour. Now, it's not in the house, and that's like the nucleus. We know the electron's not in the nucleus, but it is around the house. It's going to spend time around the house. I mean, get inside and let it, and if its dog bowl gets full, it wants to come back right away. So that's the idea of an orbital and what kind of analogy of what's going on. I like this analogy. I hope it helps you a little bit with the concept of this electron density idea. and probability of finding an electron. Let's dump knowledge, shall we? Okay, so there are certain, so I alluded to math, lots of math, and some more math and math. So there's some numbers that go in and come out of that math. We're going to call them the quantum numbers, and again, that means there's only certain allowed values. It's not continuous. That's what quantized mean. So we're going to go through 4 of these. I'm literally going to call them the first, the second, the third, and the fourth quantum number to avoid confusion. I'll put the fancier names at the top of the board here, but the first quantum number, i.e. 1, is technically called the principal quantum number. A lot of times I'll even do it in symbols. The symbol for the first quantum number is n. It's a lowercase n, and the values are 1, 2, 3, 4, 5, 6, up to infinity. From a practical standpoint, I don't think we go past 7 in this class. But 1, 2, 3, 4, 5, 6, 7. Each n value represents a shell of the atom. And it represents, and the key word here is orbital, represents the orbital size and energy. The larger the value of n, the bigger the thing is, and the more energy it has. And remember, low energy is our preferred state. So high energy is actually going to be less stable. So n equals 1 is going to be more stable than n equals 2 because it's at lower energy. So remember, low energy, ground state, that's our typical state. Excited state, that's what happens when we go into chemistry class. You can't be in chemistry class 24 hours a day. You will burn yourself out. So that's why we limit you to 50 minutes every other day. But you can supplement with these videos for as much time as you would like. All right, second quantum number, angular momentum quantum number. See, I told you they got fancy names. I'm just going to call it the second, or L. Okay, we're only going to use 4 values of L, 0, 1, 2, and 3. In theory, they can get bigger. And also, the value of L is constrained by the value of n. So the real quantum selection rules are the values of L are 0, 1, 2, 3, all the way up to n minus 1. What does this boil down to? N has to be bigger than L. Simple enough, and they're whole numbers. N and L together, when you have both values, is a subshell. So, if n equals 1, L can equal 0, and the two of these together would give me a single subshell. When n can equal 2, L can be 0, or L can equal 1. And now we have 2 separate subshells. That's a subshell, that's a subshell. So what I want to point out here is, when n is 1, we have 1 subshell. When n is 2, we have 2 subshells. I'm going to let you take a speculative wild guess. If n equals 3, how many subshells are there? Awesome. If n is 4, how many subshells? Awesome. Good. Okay, you got it. All right. And then, what does this mean? Well, this represents the shape of an orbital. And you're probably asking, well, if that represents the shape, what are those shapes? Very good question. You're very astute. Glad you're with us today. So we're going to do 0, 1, 2, 3. And it's confusing. So if I write 2, 0 like this, if I write this, is that 20? What does that mean? So we don't do that as chemists. We write 2s. This would be 2p. So the first number is our principal quantum number, and then the letter represents our second quantum number, or L. So we're going to use 4 values in this class, 0, 1, 2, and 3, and this represents the s orbital, p orbital, d orbital, and f orbital. And the shape of an s is a sphere. The shape of a p is a lot of times described as a dumbbell. Stop looking at me. I'm not the dumbbell. It's over here. It doesn't look like me. It looks like this. And then I like to say a clover leaf for D for... Hey, Clara, they're always asking me Lucky Charms. Yep, clover leaf. And F looks like a mess. This is actually... I tried to actually draw it about what it looks like. But F's look like messes, and it's beyond the scope of this class, so don't worry about that. If you see something that looks crazy, it's an F. And that is our shapes. So let's move into... We got the size, we got the shape. Let's do positioning or orientation. This is the third quantum number, called the magnetic quantum number, m sub L. And the values of m sub L range from negative L, in jumps of 1, all the way up to positive L. And if you want to get the take-home message and simplify this, what are my selection rules? N has to be bigger than L, which has to be equal to or larger than the absolute value of m sub L. And again, they'll have to be whole numbers. If I have n, L, and m sub L, I no longer have a subshell. I am talking about a single orbital. This is always one and only one orbital. This is what it takes to completely describe an orbital in an atom. And every orbital will have a unique set of numbers. So this represents positioning, direction, orientation, whatever word you want to use of an orbital. And let's go back into the numbers. and going back into this shape and orientation. So if we're in an S subshell, that means our value of L is 0, and negative L is 0, positive L is 0, and everything between 0 and 0 is 0. There is only one and only one version of this, meaning every subshell, every S subshell has a single S orbital. And it looks like a sphere. There's only one way to position a sphere. If you turn it, you can't even tell. So let's take a P subshell. P subshell, L equals 0. Now we can go from negative 1 to 0 to positive 1. This gives me 3 P orbitals in one P subshell. And what do those look like? Well, one's on the x-axis. We creatively call it px. One is on the y-axis. We creatively call it py. One is on the z-axis. We creatively call it pz. If you're wondering about the different colors, it represents the amplitude of the electron. Remember, the electron's a wave. So one color would be when the amplitude is positive, and one color is where the amplitude is negative. So if we're taking that standing wave idea, this would be one color, and that would be the other. And you can almost see a p orbital there if you look at it, where s is just going to be half a wavelength. There's my s orbital. So going back to the idea of a standing wave. Again, a little beyond the scope of the class with the math, but just to let you know why I color one half and not the other. If we go into the d's, we can go from negative 2, negative 1, 0, positive 1, positive 2. That's 5 separate d orbitals within a single d subshell. They get a little more complicated. The pictures all look the same, we just change the axis. So if it's between x and y, we call it dxy. If it's between x and z, we call it dxz. If it's between yz, we call it dyz. If it's on the axis, then we use a squared term. So if it's on the x and y, we call it dx squared minus y squared. And if it's on the z squared, this one looks funny. It's like a p with a little donut around it. That's dz squared. So there's 5 of those. The f's are a mess. The only thing I want you to know is there's 7 of those. You can see the trend. 1, 3, 5, 7. Not complicated. Oh, and if you're super curious, after SPDF, we just go in alphabetical order. A, B, C, D, E, F, G, H, I would be your next subshells. And it would just go 7, 9, 11, 13. Again, beyond the scope of the class, but if you're curious. Alright, moving right along into the fourth and final quantum number, which no longer talks about an orbital, because we just completely defined an orbital. Now we're going to talk about what lives in an orbital. The dog. No, not the puppy dog. Let's come back from the analogy. We're going to talk about the electrons. So, electron has a charge, and it moves, it spins. So if an electron spins, it creates a magnetic field. You know that whole thing they do in physics with the fingers? So I'm just going to draw it as a bar magnet, north and south. If I took a paper bag, I threw 2 bar magnets in there, and shook it around. The paper bag's supposed to be an orbital. The shaking it around is supposed to be real life. Don't you feel like you're getting shook around? Should I shake the camera to give that effect? No, I won't do that to you. Oh, earthquake. I didn't mean to do that. All right, so we shake around those magnets. When we open the bag, what are we going to see? We're going to see that they've snapped together and they've lined up north to south, south to north. Same thing with the electrons in the orbital. You can stick 2 of them in there. They have negative charges, so they want to repel. But the magnetic field does what? Attracts them, so it overcomes that repulsion. Now we can't put a 3rd electron in because it's not going to work out that way. So we get 2 electrons in an orbital, matching those magnetic fields, one going up, one going down. Up and down is arbitrary, but once one electron's in there, the other one orientates against it. So really there's only 2 orientations, with or against. And this is known as the Pauli exclusion principle. The real Pauli exclusion principle states that for every electron in an atom, there's a unique set of 4 quantum numbers. And the only allowed values for the 4th quantum number for the spin of an electron is positive 1/2 or negative 1/2, meaning spin up or spin down, or with orientation or against orientation. And what the Pauli exclusion principle really boils down to is 2 electrons and only maximum of 2 electrons per orbital. It can be empty, you could have 0, it can be half filled with 1, but maximum of 2 electrons per orbital. So, recapping what we just did. First quantum number shell, first 2 subshell, first 3 single orbital, first 4 single electron in a single orbital. N's got to be bigger than L. L's got to be bigger than or equal to the absolute value of M sub L. This is our allowed rules. The number of N equals the number of subshells. S, P, D, and F always have 1, 3, 5, and 7 orbitals in that subshell. It can have up to 2, 6, 10, and 14 electrons because we're multiplying by 2. This is all of the background we need to start putting electrons in orbitals and talking individually about atoms. Thank you so much. You are all fantabulous. Be good. Peace out.